Bessel functions. Bessel's equation will arise in Chapter 6 when we study boundary value problems in curvilinear coordinates, polar and cylindrical. You can read about Bessel's equation on page 132, a very short description, and pages 140 and 141. In this video, we'll review the general solution of Bessel's equation of order n. Bessel's equation of order n actually appears in two different forms. The basic form, or unparameterized form, where the zeroth derivative term has no lambda in front of x squared, and the parameterized form, where there is a lambda in front of the x squared in the zeroth derivative term. Although Bessel's equation will occur in the form with lambda in our work in Chapter 6, one usually first studies the solutions of Bessel's equation in the following form without the parameter lambda. So it's the unparameterized form shown in equation 1. As discussed on pages 261 and 262 in the appendix in the textbook, x equals 0 is referred to as a regular singular point of Bessel's equation 1. And because of this, we cannot use the power series method of solution of Bessel's equation as we did for Legendre's equation. Let me make a note here before we go on that this quality, regular singular point, is a definition from differential equation, and it's similar to, but it's not the same as, the Sturm-Liouville singular point. Just keep in mind there's two different ideas. There is, however, a method that generalizes the power series method, and known as the method of Frobenius, that yields modified power series solutions in the form shown at the bottom of this slide. And this is for a power series centered at x equals 0. The method of Frobenius yields two linearly independent solutions of Bessel's equation of order n, namely j sub n of x, known as Bessel's function of the first kind of order n, and y sub n of x, known as Bessel's function of the second kind of order n. Hence, the general solution of Bessel's equation of order n, these two, j sub n and y sub n, are linearly independent on the open interval. It's a linear combination of the jn's andyn's given in equation 2. The two perhaps the most important properties of the jn and yn's are the following. Two limits. The limit of the j's at x equals 0 from positive numbers is either 0 or 1. On the other hand, for all n, the limit at 0 from the positive numbers of theyn's are minus infinity. They're unbounded. Hence, in any singular Sturm-Liouville problem involving Bessel function of order n on the interval 0 to L, we must set b equals 0 on the general solution to obtain a general solution, or solutions that are bounded. So in equation 5, we have the form of the general solution. Let's next look at Bessel's equation as an eigenvalue equation when our lambda sits in front of x squared in the zeroth derivative term. To put Bessel's equation 6 in Sturm-Liouville form, we have to first write it in the form a2x double prime plus a1y prime plus a0y plus lambda y in order to use equations 7, 8, and 9 to find the weight function and the other two functions in the Sturm-Liouville form of our equation. So dividing 6 up here by x squared, dividing through by x squared, we get this equation where now a2 is 1, a1 is 1 over x, and a0 is minus n squared over x squared. Using a2 and a1, we have in equations 10 through 12 computed the weight function, and w of x turns out to be just x. Consequently, p of x and w of x are both x, and q is minus n squared over x. Hence, the Sturm-Liouville form of the given eigenvalue equation is given in equation 14. Our next observation is that, in fact, x equals 0 is a singular point of Bessel's equation of order n because Well, W vanishes at 0, P vanishes at 0, and the limit as x approaches 0 from the positive side of Q of x is infinity. Hence, in any eigenvalue problem with Bessel's equation, we need to require the solutions to be bounded at x equals 0. We'll come back to that in our next discussion, next video on Bessel's equation. For the moment, we want to plot the first 6 Bessel functions near 0. And again, the 0th one has limit 1, and all the other ones have limit 0 at x equals 0.